Okay, let's take a look at proving some trig identities. Okay, so we have a left-hand side of the equation and a right-hand side of the equation. So it says, prove that the following trig identities are equal. Sometimes you'll see RTP. If you see that, that means required to prove, which is same exact thing. Just letting you know that RTP just means required to prove. So it means that these are not necessarily equal, although most of these problems, it does work out that they're equal because otherwise you would be trying to solve it with no correct way to do it. So what we do here is we're going to have left-hand side. So LHS is left-hand side and the right-hand side. And we're just going to rewrite what we have here. And then we're going to see what we can do to simplify these so that the left-hand side equals the right-hand side. So first thing I see here, when I have to the fourth power minus squared, well, I could just factor out a tangent squared, right? So I'm going to go ahead and do that. And that leaves me with 1 plus tangent squared x. Now that gives me a very useful trig identity. And I'm going to write it up here in the corner. And that is 1 plus tangent squared x equals secant squared x. Likewise, secant squared x minus 1 equals tangent squared x. Notice that's just me moving these around so that it's now equal to tangent squared x. Okay, but in this case, we got tangent squared x times secant squared x. And once I see that, I'm like, there's a good chance I can get this to equal that if I just do a little work here on the right-hand side. So I'm going to go ahead and do that now. So that is going to mean secant squared x. If I factor that out, I have secant squared x minus 1. And just like we said over here, that Pythagorean identity tells me that secant squared x minus 1 is just equal to tangent squared x. So now I guess I could rewrite this. I could just rewrite the right-hand side, even though when you multiply something, the order doesn't matter because 3 times 4 is the same as 4 times 3. But now this is equal to the left-hand side, and then I'm done. Just the last thing you want to do is left-hand side equals right-hand side, so QED. Meaning QED is just a Latin phrase for what, thus it has been proven, or what you set out to prove, okay? So you go ahead and just write that little statement here on the right-hand side, and now we're done. Okay, let's try one more here, and this one is a little more tricky, but there's some big clues in here to what to do. The first one being this first term here. Okay, so let's go ahead and we'll go ahead and write left-hand side and right-hand side, and we'll get to work here. So we got cosine of x plus sine of x over cosine of x minus sine of x. And over here on the left-hand side, we have 2 tangent of x over 1 minus tangent squared x plus 1 over 2 cosine squared x minus 1. Okay, so there's a lot of things happening here, but the first big clue is that when I look at this 2 tangent x over 1 minus tangent squared x, that's actually the double angle tangent trig identity. So that one is that, well, it just equals tangent of 2x. Okay, so there's the double angle identity. So 2 tangent x divided by 1 minus tangent squared x is equal to tangent of 2x. All right, so that's one of them. Now, if I look at this one, 1 over 2 cosine squared x minus 1, well, 2 cosine squared x minus 1 is one of the ways that you can write another double angle formula, or trig identity, however you want to call it, is cosine 2x. Okay, so I got a very big clue here that I could do something with the right-hand side in order to get this. Now, when I look at this one, because I know that cosine 2x has, well, there's 3 different ways to write it, which are based on the Pythagorean identities, and the one in this case being sine squared x plus cosine squared x equals 1, you could also write it as cosine squared x minus sine squared x. So if I can get that in the denominator, well, I'm getting really close to solving this, because then I'll have the left-hand side and the right-hand side both with the denominator, or at least partially on the left-hand side, of cosine 2x. Well, what I'm going to do here is multiply. I know that if I have difference of squares, it's going to give me cosine squared x minus sine squared x. So I'm going to multiply by cosine x plus sine x so I can see what's happening here. Okay, so if I do that, all right, now I'm going to have, give me 1 second here. So I'm going to have on the top cosine squared x plus 2 sine x cosine x plus, let's get rid of that. Let's rewrite this. We would have 2 sine x cosine x plus sine squared x. Okay, and then on the bottom, now I have a difference of squares that I can rewrite as a double angle. Okay, so here, down here, this is going to be cosine of 2x. And then on the top, you kind of got to think about the beginning and the end of this here, right? But this, cosine squared x plus sine squared x, is just going to turn into 1. So let's rewrite this with a little more done here. So we got 2 sine x cosine x over, as we were saying, cosine of 2x, the double angle identity. Now I look at the left-hand side and I'm like, okay, well, I got cosine of 2x in half of it, but I need it over here. Well, remember, tangent of x is the same as sine of 2x over cosine 2x. So that's good, because now we're actually almost there. I'm going to go ahead and write this as one fraction here in a second. So now I'm going to have 1 plus sine of 2x. I just wrote this in the opposite direction, which will make sense in a second, over cosine 2x. Okay, now one final thing. This is all about double angles, this particular trig identities. But once I look at this, 2 sine x cosine x, that's actually sine of 2x. So now I'm done. So now I just got to rewrite this. I have 1 plus sine of 2x over cosine 2x. And now, as you can see, the left-hand side equals the right-hand side, so we'll go ahead and write that. So it has been proven, and we're done with this one.